Going already. Good. So let us begin. Let us begin with equilibrium. Now, what is basically equilibrium? Equilibrium is just talking about balance. In physics, anytime we talk about equilibrium, so let me fix up my pen and so that we can get started immediately. Now, when we talk about equilibrium, we are talking about balance. 1 minute, please. Let me see. My recording, my pen is not functioning. Now, what we're going to be looking at in this topic is we're going to be looking at the types of equilibrium that we have. We have homogeneous equilibrium and heterogeneous equilibrium. We are going to be looking at we're also going to be looking at, okay, what happens, for example, when there is change in pressure, change in temperature, change in this and change in that. Okay, what happens? What does the system do? We're going to be looking at Le Chatelier's principle also. Le Chatelier's principle is a very, very powerful aspect that is even the backbone of equilibrium reaction as a whole. I'm sorry. That is the backbone of equilibrium reaction as a whole. And UTME, most questions that they ask on equilibrium, they actually mostly ask on Le Chatelier's principle. So we're going to be looking at Le Chatelier's principle. Okay, how does the system respond to changes? How does the system respond to changes? You see, and we see that at the end of this class, you would realize that equilibrium is something that is not tough at all. That is not tough at all. So let me see whether my pen has finally responded. What is happening? I connected my digital tab and does not seem to respond to Zoom. Give me a minute. Let me see whether there's any setting I need to enable. Please, this is the first time I'm using Zoom. I often use Google Meet, but I realized that Google Meet does not give me the recording option. And the last time I attempted to record with an external app, I forgot to turn on the mic. Good, my pen is finally on. Yes, so let's begin. Now, you see, when we are looking at equilibrium, we are actually looking at how, you see, there would always be disturbance. Even as humans, it is impossible for us to stay stable. Exactly. It's very impossible for us to be stable. Let me use that language. It's very, very impossible for us to be stable. And this also affects chemical reactions. Now, take note that we have very different types of chemical reactions. We have redox reactions. We have redox reactions. We have, I'm sorry, we have redox reactions. We have displacement reactions. We should look at types of reactions also in the coming days. We have displacement reactions. We have decomposition reactions. We also have, apart from decomposition reactions, we have simple reactions. We have neutralization reactions. We have reversible reactions. And we have irreversible reactions. Now, you see, when it comes to equilibrium as a topic, the type of reaction that we look at is what is equilibrium reaction. The reaction that we look at is what is reversible reactions. Now, let me give us a very, very good example of, let me clean this space so that we can understand what I'm explaining very, very well. Please, once you don't understand something, it's a private class, just unmute your mic and just tell me that I cannot understand, please. Please, we have 16 days, no time to check time. Now, what are reversible reactions? Reversible reactions are just reactions that can proceed in the forward state and in the backward state. Now, let me give us an example of an hypothetical reversible reaction. For example, look at something like this: A plus B, C plus D. And let's look at this one: A plus B, to give us C plus D. Now, there is a very, very clear difference between these two. And what is the difference? The difference in these two is that this arrow, you can see that there's one arrow going to this side and there's one arrow going towards to the other side. There's one arrow going to this side and there's one arrow going to the other side. So it means that A plus B, when it reacts, it can proceed to give us what? C plus D. And when C plus D also reacts, it can give us what? It can give us A plus B. So that is a very good example of a reversible reaction. Reversible simply means something that can go in the forward direction and also what? In the backward direction. A reaction that can do what? It can proceed under what? It can proceed in both directions. You know, this is the right and this is the left. So it can proceed in the right direction and it can proceed in the what? In the left direction. And that is why it is called what? A reversible reaction. Please take note of that. A reversible reaction. Please, if there's any question, just use the comment box and just type it, or you can unmute your mic and just tell me that you have a question. It is very, very important. Somebody is saying it is time, sir. We have started. We have started already. I hope he's present already. I hope he's present already. I hope he's present already. Let me check the participants. Okay, just one person is absent. I think I love the turn up tonight. Now that is an example of what? A reversible reaction and what? And an irreversible reaction. Now you see, for chemical equilibrium to occur, there are certain properties that a system must possess. For a chemical equilibrium to occur, there are particular characteristics that a system or a reaction must possess. Now, the first thing is that let me use this so that we can have enough space to work. Characteristics of a system in equilibrium. Our body also, for biology students, homeostasis is an example of what? Is an example of chemical equilibrium. So take note of that. Homeostasis is an example of equilibrium. Now, properties of a system. Properties. So that I can carry this thing. Properties of a system in equilibrium. Now, the first is that chemical equilibrium can only be achieved in a closed system. It can only be achieved in a closed system. Now, by the time we get to enthalpy and entropy, probably in the next lesson, I would be explaining the different types of systems that we have. We have closed system, we have isolated system, we have open system. We have, those are examples of systems that we have. But now, you see, in a closed system, when we say something is closed, if, for example, now let me use something that is realistic. For example, if a door is closed, it means that what? Nothing can go in or out. Nothing can do what? Can go in or out. So it means that in a closed system, no substance can enter and no substance can leave. You see, a closed system must be achieved in a sealed vessel. For example, look at this. It must be covered. It must be covered. The vessel in which it can, let me say, occur in a sealed vessel. So the system is not exchanging anything with what? With the environment. It cannot take place in the open air. It can only do what? It can only take place where? In a sealed vessel. So systems in equilibrium the reactions can only take place in what? In a closed system. And just remember the definition I give for a closed system. Nothing goes in, nothing goes out. It does not exchange what? Anything with what? With the environment. Now, a very good example, another properties of a system in equilibrium is that what? Is that it can only occur in a reversible reaction. It can only occur. I'm giving us only what we need because of time. We don't have time to waste again. It can only occur in a reversible reaction. And I've explained what a reversible reaction is. I've given us an hypothetical one, A plus B, going forward and backward to do what? C plus D. So it can only occur in what? In a reversible reaction. It cannot occur, for example, let's look at this equation now, Na plus Cl minus to give us NaCl. It cannot do what? Equilibrium cannot occur here because the reaction is what? Is not reversible. But look at this equation. CaCO3 to give us CaO solid plus CO2 gas. Now, this is an example of what? Of a reversible reaction. Let me put the solid sign here. This is an example of what? A reversible reaction. So, what is this trying to tell us? It's trying to tell us, let me see whether I can increase the width of the line. It looks like this will be a little bit thick. Let's manage it. So this is telling us that this is what? A reversible reaction. And because it's a reversible reaction, equilibrium can occur. Equilibrium can do what? Can occur. Please take note of that. Equilibrium can do what? Equilibrium can occur. Now let's look at another property that is very, very, very important. Now, for those who don't understand, in endothermic reaction and exothermic reaction, I think I would talk a little bit about that so that by the time we get to that topic, it would not give us issues. Let me clean up this part so that we can be able to have more space for work. Now, another property is that change in G must be equals to 0. Now, see this question, I would advise that you go and probably read up I'll advise that you probably go and read up on this topic, but we'll touch it by God's grace. But I would advise that you just go and read up on it because UTME, there are some topics that they must ask questions from. They are married to those topics. Now, let's look at this. Now, let's look at this. Now, change in G. What is this? Change in G, sorry. Change in G refers to what? The Gibbs free energy. Change in G is equals to what? Gibbs free energy. Now, they used to say another thing they can call it, is free energy. Free energy. Free energy. Or they can call it energy available to do work. This is a very good example of what they can call the Gibbs free energy. They can call it, can you see from even the name, Gibbs free energy or energy available to do work. And now take note, this is the formula for Gibbs free energy. Change in G is equals to change in H. Is it plus or minus? I think it should be minus T change in S. Let me confirm that. I don't want to give us something that's, let me confirm that, but I think I should be correct. Change in G minus T change in S. Now, change in H represents enthalpy change. And take note that the heat content of a system is known as what? The enthalpy heat content. Now, yes, I'm correct. It is change in H minus T change in S. I'm very, very correct. Very, very, very correct. Now, change in S is what? Entropy change. entropy change. And you see this entropy change is just referring to the rate of disorderliness in the system. Now, let me quickly say something around entropy change. Now, you see, gaseous states has the highest entropy. Please take note of that. You know, the molecules of a gas are far apart. Gaseous theory of matter, or kinetic theory of gases, exactly. So gaseous state has the highest entropy. Give me a minute. Somebody wants to, I think somebody, okay. Please, I hope you are inside the group already. Boss Tolu, I hope you are inside already. Let me see. I hope you are inside already. It's very, very important that everybody is carried along and that nobody is missing anything, please. It's very, okay, yeah, he's present already. Okay, yeah, you're welcome. Please, I hope we are getting what I'm explaining. Please use the comment box. I hope we are getting what I'm explaining. Good. So let's continue. You almost passed. I'm expecting at least above 85 from everybody here in chemistry. It's possible by God's grace, and we would all have it. By God's grace. Now, gaseous state has the highest entropy. Solid state has what? It has the lowest entropy. Please take note of that. Now, the T is represented by what? The T is temperature in Kelvin. Please take note. Temperature in Kelvin. Take note of that. The T is represented by what? Temperature in Kelvin. Very, very important that you take note of that. I think the person that said the time limit of Zoom is more than 30 minutes, the person is very, very, very correct. Thank you for that. I really, really appreciate. In fact, this would have made my work easier since. Thank you for that. Now, T is represented by what? Temperature in Kelvin. Now, let us look at something. Take notes. Let me draw caution sign so that you can be able to, don't mind my caution sign. Take notes, very, very important. See, this thing, they like is JAMB's favorite topic. Take note of this. When change in G is negative, that means that the reaction is feasible. Please take note of that. When change in G is positive, reaction is not feasible. That means reaction will not occur. Reaction, except if forced, is not feasible. Reaction is not feasible. When change in G is equals to 0, it means that reaction is in equilibrium. Take note of that. By the time we get to enthalpy, entropy, I would shed more light. Somebody saying something? Okay, that time limit is 40 minutes. That means, please, once the call trips off, what we should do is just come on again. Just come on again. When the call trips off, just come on again. Yeah, so we'll use this same link again. Just come on again. I think by the time it's 8:35, I would shut down the call. So we'll just use that same link again. No need to stress ourselves. When it's 8:35, I would shut down the call. Then you all should just join through the new link, through that same link again. Now, so this is, now I said it. So one of the characteristics of a system at equilibrium is that what? Change in G equals what? Equals 0. And I've explained what change in G is all about. Now, take note of this. I would shed more light on it by the time we reconnect. Catalysts does not have an effect on the can you see, they've even told us running out of time. So let's leave the call and just reconnect again. let's leave the call and just reconnect again.